Hello and welcome to this video for CE 108. In this video, what we're going to do is review an example of problems to calculate the deflection of a beam, the lateral deflection of a beam that is subjected to some bending. So in this case, the idea is that we will use the method of integration to integrate the external distributed load that is applied to a beam. We need to integrate this 4 times. If we integrate the distributed load 1 time, we get the internal shear. If we integrate it 1 more time, we get the internal moment. If we integrate it 1 more time, we will get the angle of the beam with respect to the horizontal axis. And if we integrate it a 4th time, then we will get the lateral deflection. So we will see an example of such a problem in the case of a triangular distributed load. Let's consider the following beam, which goes from minus L to plus L. It's attached to a pin at x equal minus L and a roller at x equal plus L. And then it's subjected to a triangular distributed load, which is linearly changing. So it's a triangular shape. Remember that the positive sign convention is that the load is positive if it's pointing upward and it's negative if it's pointing downward. So here in this case, the load is initially pointing downwards between minus L and 0. So it's negative. The intensity of the distributed load is minus W naught at minus L. And then between 0 and plus L, the distributed load starts to point upward. So it's becoming positive and eventually reaches an intensity W naught at x equal plus L. So in this case, what we're going to do is integrate this distributed load 4 times in order to get the deflection. Remember that in this case, in deflection problems, this is the only case where we do not have to find the unknowns and calculate the value of the unknowns using the condition of equilibrium. So this is the only case where, irrespectively of whether the problem is statically determinate or indeterminate, we don't need to find the value of the unknowns. We can directly follow the method, and this will directly allow us to find the value of the deflection without the need for the unknown reaction from the supports. So here in this case, the general method is that after you have drawn the free body diagram, we will start by identifying the potential source of discontinuity. So that's the first step. Is there any discontinuity in this case? And so in this case, discontinuity are going to come from either concentrated forces or concentrated moments that are applied inside the beam, not at the extremities. Here in this case, we have the pin and the roller that potentially can induce concentrated shear force, but they are applied at the edges, so they are not applied inside the beam. So hence, they won't result in any discontinuity. And similarly, we have the distributed load that is applied, but distributed load do not induce any discontinuity. So here in this case, there is no discontinuity, so we don't have to write any continuity conditions. So there is no discontinuity in this case. Step 2, we need to find the limit condition. So the limit condition are going to be useful to integrate, to find the integration constant when we integrate the load 4 times. We're going to integrate the load 4 times, so we are going to need 4 integration constants, and we will get 2 constant per extremity. So here we have 2 extremity for this beam, so we need 2 limit condition per extremity, which will give us a total of 4 limit conditions, which will allow us to find the 4 integration constants that we will need when integrating the load 4 times. So here in this case, so we have 2 cases. So we have x equal minus L and x equal plus L. Those are the 2 edges of this beam. So here at x equal minus L, the beam is attached to a pin. So necessarily, even if we do not know what is the resultant force applied by the pin at this point. What we know for sure is that the beam remains attached, vertically attached to the pin. The pin prevents the beam from going up and down at this point. So necessarily, the deflection of the beam at this point will be 0. Same thing at x equal plus L, the beam is attached to a roller, so the beam cannot go up and down. This is prevented by the roller. So necessarily, the deflection of the beam at plus L is going to be equal to 0. So in terms of slope, we don't know anything because the beam is not prevented from rotating. The pin and the roller do not prevent the rotation of the beam at those points. So we do not know what is going to be the slope of the beam with respect to the horizontal axis at those points. We also do not know what is the value of the internal shear at those points because the pin and the roller are going to create a vertical force to prevent the beam from going up or down. So we do not know what is the value of the internal shear. However, we know that the pin and the roller do not prevent the beam from rotating. The beam is free to rotate about those 2 points. So hence, it means that there is no external moment applied at those points. The pin and the roller do not create any external moment. So since at the edges, the external moment becomes equal to the internal moment, provided that the external moment are expressed with the right sign convention. Here in this case, since there is no external moment, then the internal moment at minus L and the internal moment at plus L are both going to be 0. So those are the 4 limit conditions that we will need to find the 4 integration constant that we will get while integrating the distributed load. So now that we have the continuity condition and the limit condition, we have everything we need to start doing the 4 successive integrations. And again, in this case, we do not need to find the value of the unknowns. So here, the first step that we will need is to express the distributed load. So here you need to be careful because if you make a mistake when expressing the analytical function that gives you the distributed load, then everything else will be potentially wrong if you carry this, if you have some propagating errors. So here in this case, the distributed load is a linear function. It's a function that initially is equal to minus W naught since it's pointing downwards at x equal minus L. And it's linearly increasing, becoming 0 at x equals 0, and then becoming equal to plus W naught at x equal plus L. So it's a linear function that is linearly increasing. It's equal to 0 at x equals 0, so we can express this distributed load simply based on the slope of this curve. Here, the slope of this curve is the increment of the distributed load is W naught. Between 0 and L, the load increased by W naught. The increment of x is L in this case. Between 0, x equals 0 and x equals plus L, the distributed load increases by W naught and x increases by L. This gives you the slope. So we just need to multiply the slope by x to get the value of the distributed load. If you are not sure how to get this formula directly, or if you have another type of distributed load that is triangular, you can always use the fact that this distributed load is a linear function, so you can express it as ax plus b, a linear function, and then you just need to find the value of a and b. So for example, in this case, we know that the distributed load at 0 is equal to 0. On the other hand, since if we replace x by 0, so that gives us a times 0 plus b, so necessarily b is equal to 0. And then if we have to find the value of a, we can use the fact that the distributed load at x equal plus L is equal to W naught, but the distributed load at x equal plus L is also equal to A times L plus B, but B, we already found that it's equal to 0. So in this case, that gives us that A is equal to W naught divided by L. So based on this, we find the same formula that the distributed load is equal to W naught times X divided by L. So we can always find the value of a linear distributed load simply by expressing that it's a linear function and then using the value of this distributed load at 2 points. And based on this, you can find the value of the slope and the value of the intercept. So based on this, what we're going to do is start expressing the load and integrate this load 4 times. So based on this, we can start by expressing the fact that the load is going to be related to the fourth derivative of the deflection. So eventually, what we want to find is the deflection, and the load is going to be equal to EI, Young's modulus, times moment of inertia about Z, times the fourth derivative of the deflection with respect to x. So here the load is what we know, and the deflection is what we want. So we will start by expressing the load, and then we will need to integrate this 4 times in order to get the deflection. And we can write it like this, so that we can integrate member by member. And if we integrate this member by member, if we do that 4 times, eventually we will get the Young's modulus E times the moment of inertia I times the deflection, which is what we are looking for. So let's start with the load. So in this case, the load, we just said that the load is equal to W naught times X over L. So based on this, now we can move to the next step, which is, now that we have expressed the load, we are going to integrate it member by member. So if we integrate the first term, E and I, those are constant terms if the cross-section and the material are constant. Now we integrate the fourth derivative of the deflection, we will get the third derivative of the deflection. If we integrate the load, now we are going to get the internal shear, since the derivative of the shear respect to x is given by the internal load. And now we just need to integrate this internal load. So for the first term here is proportional to x. So when we integrate this, we will get x2 over 2. So we are going to get 1/2 W naught over L times x2. And here we are getting an integration constant. So we're getting an integration constant coming from the fact that when we integrate this function, we need to find a function that once differentiated gives you back this distributed load. And here in this case, if we take the derivative of V, irrespectively of what is the value of C1, its derivative is going to be equal to the distributed load. So whenever we integrate the function, we always have this integration constant. So usually we have to use the limit condition to find the integration constant. But here in this case, we have no limit condition in terms of the internal shear. So we cannot find yet the value of C1. So here we will need to keep C1 as a variable for now, and we will be able to find the value of C1 by continuing this integration. So now we can move to the next step, and we can again integrate this function. So if we integrate the first term, we get now the second derivative of the deflection with respect to x. If we integrate the internal shear, now we are going to get the internal moment. So now we need to integrate this formula here. So if we integrate x2, we are going to get x3 x cubed over 3. So that's going to give us 1 over 6 times W naught divided by L times x3. And then we have C1. C1, we don't know its value yet, but it's a constant. So if we integrate this, we are going to get C1 times x. And now we're going to get a new integration constant. We are again integrating one more time. So every time we integrate, we get a new integration constant. So now we need to find the value of C1 and C2. Here, now at this point, we have some limit condition involving the internal moment. We can use first the fact that the internal moment at x equal minus L is equal to 0. And we can also use the fact that the internal moment at x equal plus L is also going to be equal to 0. So those two limit conditions are going to give us some equation that we can use to find the value of C1 and C2. So we know that the internal moment at minus L is going to be equal to 0. So we can, and on the other hand, we have an analytical expression for the internal moment. So here we can just replace x by minus L, and say that at minus L, the internal moment has to be equal to 0. So if we do that, we can take this expression, replace x by minus L, and set this to be equal to 0. So this is going to give us, so x3, if we replace x by minus L, that gives us minus x to the power 2. So based on this, sorry, minus x to the power 3, sorry, so that gives us minus O big N naught L3 divided by 6L. So that's what we get for the first term. Then if we replace x by minus L, we are going to get C1 times L minus C1 times L, and then we get C2, and this is equal to 0. Now if we do the same for the second limit condition, again, we replace x by this time plus L, and we set this to be equal to 0. So this is going to give us this time plus omega naught L3 divided by 6L plus C1 times L. Now we replace x by plus L plus C2, and this is equal to 0. So this gives us a system of two equations, equation 1 and equation 2, that we can use to solve this system and find the value of C1 and C2. So for example, here what we can do is to take the sum of equation 1 plus equation 2. If we do this and we sum member by member those two equations, the first two terms disappear, they cancel out each other, and we only get 2 times C2 is equal to 0 plus 0, which is 0. So in this case, we get that C2 is equal to 0. And then, for example, we can use now equation 1 to find the value of C1. So in this case, if we use equation 1, we can, since C2 is equal to 0, we can say that C1 times L is equal to minus omega naught. We can simplify by L, so L2 divided by 6. And so again, if we simplify by L, that gives us the value of C1. So C1 is given by minus W naught L divided by 6. So we have find the value of the two integration constants, C1 and C2. So now we have everything we need to express the moment. So the moment is equal, here the internal moment is equal to 1 over 6 W naught times x cube over L minus W naught L over 6 times x. Okay, so this is now the expression of the moment, and we will need to restart from there, from the next step, to now integrate the moment into the slope of the curve with respect to the horizontal axis. So now we need to repeat that operation one more time. So now if we integrate this, we're going to get EI times the first derivative of the deflection with respect to x. This gives us something related to the slope of the curve, the angle that the elastic curve makes with respect to the horizontal axis. Here, however, in this case, the angle with respect to the horizontal axis is given by the slope, and the slope is the derivative of the deflection with respect to x. So here what we get is not directly the slope, but we get EI times the slope. So EI times the slope of the curve with respect to the horizontal axis. And so now we need to integrate this function. So we integrate an x cubed, so we're going to get x4 over 4. So altogether, this is going to give us 1 over 24 W naught divided by L times x4. Now we integrate a term that is proportional to x, so we're going to get x squared over 2, so 1 over 12 W naught L times x2, and again we get an integration constant x3, c3, sorry. So now in this case we need to use the limit condition, but in this case we have no limit condition related to the slope, related to the angle with respect to the horizontal axis. So here we need to again keep c3 and continue integrating, and then we will be able to find C3 at the next stage of this integration. So now if we integrate this one more time, we integrate the derivative of the deflection, we get simply the deflection. So again, if we integrate the slope, again, the derivative of the slope is the deflection itself. So now we have reached the last step, which is what we wanted, that is to say the value of the lateral deflection. So now we need to integrate this analytical expression. So we integrate a term that is proportional to x to the power 4, so that gives us x to the power 5 divided by 5. So 24 times 5, this is 24 times 10 divided by 2, so 1 over 120 times x naught divided by L times x5 minus the next term is an x2, so it's going to become an x3 divided by 3. So and this gives us minus 1 over 36 W naught L times x3. We have the constant C3. We do not know what it's equal to, but it's a constant. So when we integrate it, we get C3 times x, and we get a new integration constant C4. So now we have two constants, C3 and C4, and we have two limit conditions. Now we know that the deflection is equal to 0 at x equal minus L and x equal plus L. So this is what we are going to use to find the value of C3 and C4. So we can use the fact that the deflection at minus L is equal to 0, and then the fact that the deflection at plus L is equal to 0. Replace x by minus L and by plus L, and use those two equations to find the value of C3 and C4. So the first thing, if we take the deflection, replace x by minus L. So for x5, we are going to get minus L to the power 5. So if we simplify by L, what we are going to get here is W naught divided by 120 times nothing. If we simplify by L, and we get this times L to the power 4 with a minus sign. Next term, if we replace x cubed, we replace x cubed and we replace x by minus L, so we will get minus L cubed. So altogether what we will get is minus L cubed times L, so that's going to give us an L4. So altogether we get W naught times L4 divided by 36. And here, since we have a minus sign in front of this, and since x cubed taken at minus L gives us minus L cubed, we get a positive sign. C3, so we replace this x by minus L, so we get minus C3 times L plus C4 is equal to 0. Now let's do the same, but this time by replacing x by plus L based on the second limit condition. So we get W naught divided by 120 times L to the power 4 minus W naught L to the power 4 divided by 36 plus C3L plus C4 is equal to 0. So now we get again two equations, number 4 and number 3. And again, we can combine those two equations to find the value of C3 and C4. So here, for example, what we can do is, again, we can sum up those two equations. So if we sum equation 3 and 4 member by member, the first three terms are going to disappear, and we only get 2 times C4 is equal to 0 plus 0. So C4 is equal to 0. And then, for example, we can use equation 3 now to find the value of C3. So if we use this equation and we divide everything by L and put C3 on the other side of the equation, so we get that C3 is equal to W naught L3 divided by 36 minus the other term, which is W naught L3 divided by 120. So we can put everything with a denominator of 360. So that's going to give us 10 minus, so this one we need to multiply by 3 times W naught L3. So this gives us that C3 is equal to 7 W naught times L3 divided by 360. So based on this, we have found the value of C4, the value of C3. So now we have everything we need to express the deflection. So based on that, we can restart from there and just replace the value of C3 and C4 by the constant we just found. So we can write the fact that the deflection here is equal to 1 divided by EI, the Young's modulus times the moment of inertia, times, so the first term is W naught x5 divided by 120 times L. The second term is W naught L x3 divided by 36. Next term is C3 times x, and we just found the value of C3, so it's 7 omega naught L3 divided by 360 times x, and C4, we just found that C4 is equal to 0. So that gives us the value of the deflection in terms of x. And again, here in this case, all you need to do to find this deflection is first integrate 4 times the distributed load. When we do this, we find 4 integration constants, C1, C2, C3, and C4. And so for this, the only thing that we need to do to find those integration constants is to use the 4 limit conditions that we have. Those 4 limit conditions will give you exactly enough information to find the value of those 4 integration constants. So altogether, by integrating the load, which you always know the distributed load, it's always something that is known. So you can always integrate it 4 times and then you always get 4 limit conditions, so 2 limit conditions per extremity. So you have everything you need to analytically integrate and find the value of the integration constant to find eventually the value of the lateral deflection. At the end of deflection problem, it's always a good idea to check that the dimension of each of the terms that you get is the same to make sure that you haven't done any calculation mistakes. So here for each of those terms, they are homogeneous to the distributed load W naught times a distance to the power 4. So for each of those cases, we get W naught times distance to the power 4, W naught times distance to the power 4, and W naught times distance to the power 4. So it's a good sign that at least there is no obvious calculation mistake. So it's good to always check for any problems in CE 108, but especially for deflection problems where you have to do those series of integration to ensure that there is no mistake with the power of x or with the constant that you're calculating. It's always good to double check the dimensions at the end of solving the problem to make sure that your final equation has the correct dimensions.